back. This is an extension of last video with some more advanced topics about the physics of baton twirling. So if you have not seen that one yet, then I suggest you go take a look at that. And if you have seen it, then continue on. So the first video we're going to take a look at is the video of me spinning the knives, and we have some constants and values calculated from our first video that I'm not going to recalculate, but the radius of the knives when they're hooked together is 1.3716 meters, the angular velocity is 6.9 radians per second, the mass is 1.36 kilograms, and the time is 5.0 seconds. Moving down below, you can see that the angular acceleration, just used by our simple kinematics formulas, is found to be 1.4 radians per second squared, and the tangential acceleration is 1.89 meters per second squared, because that's just the radius multiplied with the angular acceleration. And I tried to use two significant figures for all of our values in here, but obviously here I forgot, so just keep in mind that this would, with the use of significant figures, would round to 1.9 meters per second squared, so sorry about that. Moving down below, you can see the calculations for tangential force, which is mass times the tangential acceleration, and that ends up being 2.6 newtons. And on the next slide, we can see the centripetal force, which is a more complicated formula, which is m tangential velocity squared over r, and we can calculate the tangential velocity by multiplying r by omega, but one of the r's cancels out, so it's a much simpler mr omega squared now, which leads us to 89 newtons for the centripetal force. The next video we're going to take a look at, like last time, is the video of me throwing the knives. So again, our value is calculated in constants. The radius is 1.3716 meters when hooked together. The displacement is 2 pi radians because they made one revolution in the air, a full revolution. The time is 1.5 seconds. The angular velocity is 4.2 radians per second. Angular acceleration is 2.8 radians per second squared, and the mass is 1.36 kilograms. So, moving on to the next slide, since some of our work got cut off, speaking of work, the work is calculated to be, right now we're using the torque times the displacement. So that ends up being 15 joules. And we've calculated the torque by using the moment of inertia times alpha, the angular acceleration, and you'll see how to calculate the torque individually in the next clip, which is looking at me in the high toss. So now we're looking at the momentum, and again, next slide because it got cut off. But first, translational momentum, which is m over v, and again, we're going to make v r omega. So momentum ends up being 0.24 kilogram meters per second. Rotational momentum is L equals moment of inertia times omega, and for this particular particle, I guess you want to call it, since it's moving on its own axis in the air, the axis going through the center of the knives when hooked together, the specific moment of inertia is 1/12 times the mass times the length squared, rather than 1/2 mr squared. So there's something to keep in mind. That'll go for this and for the high toss, but you'll see that noted there. And after using the moment of inertia times the omega, that ends up being 3.6 kilogram meters squared per second for the rotational momentum. And finally, for the tossing of the knives, we're going to look at the kinetic energy. So we're going to utilize the moment of inertia, which is found on the previous slide, but it'll be 1/2 times 4.2 times 3.6, which is 7.5 joules. And you can also see here that I kind of played around with the equation a little bit. The kinetic energy equation kind of resembles the rotational momentum equation, because rotational momentum is L equals I omega, and kinetic energy is 1/2 I omega squared. So you can factor out the rotational momentum and just make it 1/2 omega times L, which makes it a lot easier. So that's where I got the 3.6 from the previous calculation. Lastly, we're going to take a look at the video of the high toss. So again, we have some constants. Since it's just a baton, the radius is 0.3429 meters, so quite a bit smaller. The displacement is 8 pi radians, however, so that's a lot bigger. The time is 2.0 seconds. The angular velocity is 13 radians per second. The angular acceleration is 6.3 radians per second squared. And the mass is 0.453592 kilograms. And if you guys want to see like the angular velocity, the angular acceleration, how those are calculated, just take a look at the first video, which I'll put the link down below. So first we're going to find moment of inertia, as I mentioned before, because this is something moving in the air with an axis going through its center, a rod. It's 1/2 mass times the length squared, so since it got cut off, it is 0.018 kilograms meters squared. Finally, we're going to take a look at the torque, and the torque is the moment of inertia times alpha, the angular acceleration, which you got from the first slide. So we'll take the two values from above and multiply them together to get 0.11 Newton meters for our torque. So that brings us to the end of our video. I hope you learned something new again, maybe even about baton twirling as well. That's pretty much all I have, so I hope you have a wonderful day.